Earlier, we looked at this diagram as an illustration for the development and use of laboratory automation technologies. Now we'll examine it in more detail. Not too many years ago, when someone talked about laboratory automation, a lot of the focus was on connecting experiments and instrumentation to computer systems. Interfacing these systems was a major concern. That work generally broke down into two areas: data acquisition and control, and communications. We discussed data acquisition and control when we were looking at the connection of the real world to computers. The real world consists of signals in the form of voltages, physical movements such as rotation of a shaft that have to be converted into voltages, or the opening and closing of switches. If we want to read voltages, or control things through the generation of voltages, we use analog input and output. Reading a voltage is done through an analog to digital converter, a device that measures the voltage and represents that voltage by a digital value. If we want to generate a voltage to control a device, we use a digital to analog converter. Switch closures are sensed using digital input and output. Digital inputs can be used to determine whether or not a switch is open or closed, and digital outputs can be used to open and close a circuit. For example, turning an LED on or off. Instrument communications take place through four types of devices. RS-232 and similar protocols are used for serial data. At one point, this was a very common way of making connections between computers and intelligent devices, since the device can be made to appear as a keyboard-printer combination and programmed the same way we would talk to or read from those types of devices. The IEEE 488 instrument bus is commonly used in electronic test systems. For a short time it was tried in chemical laboratory systems, but never really caught on. It is an excellent system for controlling communications between intelligent instrument devices. With the availability of reduced-cost bus-based systems and network systems, such as the USB buses and Ethernet, instrumentation can directly connect to networks and operate as fully intelligent devices. Today, in most laboratories, there is little concern about interfacing using analog to digital conversion. Many people will think this is ancient history, and not something that should be concerned about in modern laboratory work, thinking that all instruments are now digital. To some extent they have a point, but there are areas, particularly in research when new techniques are being developed, where this is still very much a concern. The need to understand analog to digital conversion and the role of control systems is central to fully understanding laboratory instrumentation and its development. As an example, we'll take a look at a device called the single pan balances and scales. The purpose of a single pan balance is to determine the weight of an object. It works by placing the object on a pan and then adjusting weights on sliding scales until the arm shows the system is in balance, and then you can read the weight from the scales. These devices have been part of laboratories for decades, but today they've been replaced by electronic single pan balances that improve productivity and make the process easier and less error-prone. The same logic applies to the typical bathroom scale, which in effect is a single pan balance. The old mechanical balances with rotating scales have been replaced by electronic balances that give you your weight in numerical form. The balances in the previous slides have been replaced by the electronic versions, which have differing capacities and precision. Someone might look at these and say, well, these are just digital instruments, when it is just the packaging that makes them look that way. These are, in fact, a mixture of analog and digital circuitry that gives us a good model for understanding a lot of laboratory instrumentation. It's just a matter of looking under the skins. If we open up the balance, we can take a look at the components inside and see how they convert signals from the analog world to the digital world, and also control the operation of the unit. We'll start by putting an object on the pan of the balance. The supporting shaft under the pan sits on top of a load cell. There are different types of load cells. The most common is a strain gauge. The strain gauge responds to the weight of the object by converting the force exerted by the weight of the object into changes in electrical resistance. As the weight changes, so does the resistance. Changes in resistance are converted to voltages with a simple electrical circuit. This combination of a device that converts forces in the real world to voltages is common in laboratory work. For example, if we wanted to measure the movement of a pendulum swinging back and forth on a shaft to an electrical signal, We would attach a variable resistor to that shaft that supports the pendulum and use a circuit that converts resistance to voltage to get that electrical signal. As the shaft rotates, the value of the resistance changes, which can be converted into a changing voltage. Those voltages can be measured with an analog to digital converter, and what was the weight is now represented by a digital value. The digital value is reported to the balance's digital control subsystem. The control subsystem carries out all the functions that we normally associate with operating the balance. Once the signal representing the weight has been measured and is converted over to a weight in grams, for example, it is shown on the digital display. It is also stored internally if it needs to be used for some other purpose. The control system also provides communications capability to outside devices, such as a computer through an interface, which might consist of a USB port, serial port, or Ethernet connection. This combination of an analog measuring system and digital control communication system packaged together is common in modern instrumentation. For someone doing laboratory automation work, it is useful to understand how the equipment actually functions and what is actually going on in order to address instrument interfacing, communications, and automation. Almost all instrument measurements are based on reading voltages that have to be converted to digital values before computers can work with them. The need for analog to digital conversion is always going to be there. It just may not be that obvious that it's going on. The next major stage in the development of computer systems for laboratory work was the development of instrument data stations. In the 1960s, PerkinElmer Corporation began experimenting with computer systems for data acquisition, analysis, and reporting. As we'll see in the section on instrumentation, analyzing instrument output can be a laborious task. Using computer systems to do the work relieves people from a lot of tedious work. We'll be looking at these systems in more detail later. The initial products that came to market were simple devices to do measurements from a single instrument and then report them to the user. As computer systems became more sophisticated, so did the software. Vendors developed computer systems that had the ability to attach several similar instruments to one computer, acquire data from each of them, analyze the data streams independently, and produce reports for the user. These evolved into full client-server systems that allowed not only data acquisition from a number of instruments, but also allowed several users to access the data and work with it in the laboratory or from remote locations. The next type of technology we will take a look at is that of robotics and liquid handling systems. Sample preparation, that is taking samples, dissolving them, and getting them ready for instrument measurements and assays, is a labor-intensive and tedious activity. As we've seen earlier, discovery research can look at many thousands of compounds with tens of thousands of tests. Using robotic systems, laboratories can do the work much faster and at lower cost. Of the sciences, life science industries have the most sophisticated approach to robotics and liquid handling systems. The commercial work in laboratory robotics began with companies such as Zymark, PerkinElmer, and Hewlett-Packard. In each case, the approach was the same: provide components and let the user design and build the robotic system. That didn't work very well, and many attempted projects found themselves abandoned. The robot systems that were developed were based on two styles. The center image shows a robotic system that had a fixed base for the robot, with an arm that could swivel 360 degrees, raise and lower itself, and used a series of grippers to hold different types of objects. The gripper system was designed so that the robot can change them under program control. The second style was promoted by Hewlett-Packard. It used an arm that traveled along a rail attached to a laboratory bench. Equipment that the robot had to interact with was laid out on the bench, and the system was programmed to work with them. Because the robots had to learn where things were, every implementation was unique and required training and adjustment. This is a very time-consuming process. Zymark created a technology, shown in the center image, that made the problem a bit easier to deal with. Each type of device that the robot had to interact with was laid out in a series of sectors around the robot base. Once the robot knew what the device was and had a reference point for its location, it could automatically calculate any other positions needed for things that it had to connect to. Other companies such as Tecan and Beckman focused specifically on liquid handling and took more successful approaches that we'll look at in a few slides. The problems found while developing robotic systems came from several sources. First, the laboratory processes that the robot was expected to replace were not understood as thoroughly as they should have been, and in some cases the equipment used was difficult to work with, using anything but a human hand. Second, much of the robotics development work was done by scientists who took an experimental approach to design and implementation instead of a systems engineering methodology. Third, the potential for automation was not examined before the project was done. People assumed that they could automate something without understanding all the details that went into successful automation programs. As noted above, there was a need to make adaptations to equipment which was expensive and not always successful. Too often, systems were a combination of third-party products that were not designed to work together. Having them function as a unit was left as an exercise for the user, and a change in one component, for example a software upgrade, could completely stall the entire system. There have been notable successes in the field of laboratory robotics. The image on the left shows part of an autosampler, a device used to select sample vials and automatically inject them into an instrument. These have been very successful and are widely used, in many cases without even thinking about the engineering that went into them. The other images show equipment from Caliper Life Sciences that is used in the preparation of sample plates for assays and other testing. Similar pieces of equipment are available from vendors such as Tecan and Beckman. Aside from being well-engineered products, the success of liquid handling systems in life sciences has depended upon a single element. The sample container consists of a standardized plate designed to hold large numbers of samples, each of which has its own sample well. Standardizing the size and shape of the plate and the arrangement of the sample wells has led to the development of compatible products from a number of vendors that can be used in automated systems. The same standardization doesn't exist in the other sciences because of the wide variety of sample types that exist. This diagram shows another interesting example of laboratory robotics. This is a system designed by Baytech International and is a variation on the autosampler mentioned earlier. In the center of the diagram is a rectangle identified as a sample bank. Samples enter the sample bank for preparation and distribution to a number of instruments. Samples travel from the sample bank through the pneumatic tubes to each device, which can be hundreds of feet away from the sample bank itself. The system allows for all sample preparation to be done in one place, which is particularly useful if you're dealing with hazardous materials. The successes in laboratory robotics have resulted from processes that are well understood, well engineered, the potential for laboratory automation determined as being realistic, using equipment that is designed and adapted to fit the application, and components that are integrated for use together. The following video, which has no soundtrack, was provided by Agilent to show how the robots work. It doesn't show any particular application, but does give you an idea on how flexible and fast these systems can be. The video shows the robots working with the sample plates we described in the previous slide. While earlier robotic systems relied on physically locating objects and reference points, more modern systems allow for both physical and numerical adjustments to locations and movements. This approach allows for better modeling of systems operations, testing, and updates as required. It also allows a robot to be put to use while changes are being considered, instead of taking the system offline. The actual robot programming can be updated once adjustments are completed. Most robotics applications tend to be fairly straightforward and deal with a predetermined sequence of steps that is repeated over and over. At the 1984 PitCon conference, an annual laboratory trade show, the results of a collaboration between Digital Equipment Corporation and Zymark was shown. The problem that we wanted to address was the ability for a computer to take over the control of the robot and adapt the robot's behavior as the experiment progressed. One common experiment that's been done in laboratories is titrations. You may have done one in high school chemistry, where you added a liquid, a drop at a time, to a second liquid in a flask or beaker until a color change occurred that showed when the titration was completed. When this process is carried out with robotic systems, the robot does everything and returns a single value for the results of the analysis. In this experimental version, the robot would carry out sample preparation steps and add titrant under the command of the host computer system. The computer system would get the results of each liquid addition and calculate the next addition, repeating the steps until a titration was completed. This allowed the analyst to see the development of the titration curve as the experiment progressed, something not normally seen when robots carry it out. In addition, the speed of the analysis was increased because the larger amounts of liquid could be added where changes were very small, and smaller amounts added where changes were large. So aside from being a nice demonstration, what does this have to do with the real world? When robotic systems are used to prepare samples and run tests, they keep doing it over and over and over until the samples are exhausted. It isn't until an analyst reviews a report that they can detect problems that may require rerunning the analysis. This can waste time, materials, and delay the release of the results. If the computer system can analyze the results as they are developed, problems can be detected quickly and corrective action taken. Corrective action might include rerunning a test or stopping the system from operating to avoid wasting materials. The demonstration showed that the communications capability and the ability for the computer to control the robot was not only possible, but practical. If you are considering robotics projects, there are a number of things you should keep in mind. First, this is not like buying instruments, where the vendor has prepackaged capabilities that can be easily demonstrated. This is a process engineering project that requires planning, training, and more planning to make sure you can realistically accomplish your goals. Doing the training during the planning process is important. While the training is underway, you may learn of capabilities that you weren't aware of that may increase the likelihood of success for your project. You may also find out some things that you thought were possible are not as easy to do. When you're looking at robotics projects, there are three types of implementations that you can deal with. The first are turnkey systems, where the vendor has done all the engineering, you just put it to work. Auto samplers used with instrumentation are one example of turnkey systems. Another type are those that consist of fixed hardware systems that have programmable operations. Basically, the system has certain capabilities built in, and it's up to you to decide how you want to take advantage of them. There are auto samplers on the market which do more than select and inject samples. They can be used to heat samples, add material to them, and carry out fixed function steps that the user programs. They provide a lot of capability at a reasonable cost in a small space. 15 years ago, the same capability would have taken a large experimental setup that could have taken months to develop. The third type is the more ambitious, where you, or a third-party contractor, is developing a system specifically to meet your laboratory's needs. These systems can be expensive to develop, support, and maintain. In life sciences applications, when the testing is based on standard sample plates and using components designed to work with those plates, the likelihood of success is considerably increased. Standardization has made the problem a lot simpler. The biggest problems will come in developing compatible control systems that have to interact with multiple products from different vendors that may independently require upgrades and modifications. The next section we will consider comes under the heading of Laboratory Informatics. Over the past few years, this is the place where a major amount of emphasis has been placed, where companies are considering laboratory information management systems and electronic laboratory notebooks. We'll start by looking at laboratory information management systems. To illustrate the use of a laboratory information management system, or LIMS, we will come back to an example that we used earlier, that of a printing or copying operation that also includes binding, large-scale graphics, posters, and graphics design work. One problem that the business like this has is keeping track of the work in progress, what work has to be done, and answering customer inquiries about the status of their work. That same problem exists in testing laboratories, where samples come in, need to be scheduled, work lists generated, reports issued, and being able to answer questions from people about when their work will get done. That is the task of a laboratory information management system. That's what it's designed to deal with. In addition to managing workflow, LIMS contain all of the test results for the work the laboratory has done. Just as a customer management system is the operational hub of a printing operation, a LIMS is the hub of a testing laboratory's operations. The LIMS database is the place where information about samples coming to the laboratory are logged, and the sample's receiving status is noted. It's possible for work to be logged into the laboratory before the samples arrive so that people know what is expected. When the samples come in, its arrival is noted, and the system is aware that this material can now be processed. The database is also used to develop work lists for analysis. If someone is carrying out a particular test, they can ask the system for a list of all samples that need that testing done, get them in priority order, then find out where the materials are that they need to work with. As testing is completed, the test results can be entered into the system. The normal operation for the laboratory is to have someone other than the analyst review and approve results, and once that is accomplished, the results can be reported. In small laboratories with limited testing, paper systems were adequate, but as laboratories grew, the testing became more complex, and the sample volume increased. Electronic systems provided a lot more capability and improved the administration of laboratory work. They also made it easier to meet the demands of regulatory requirements. As we talked about earlier, automation systems are built around processes, and LIMS database products are a perfect example of software built to implement a specific process. In the 1980s, when LIMS first became popular, there was a fair amount of confusion about what they actually did and what was necessary to understand and buy them. Adding to the confusion were differences in terminology used by different vendors. That isn't too surprising because the words Laboratory Information Management System would seem to cover a wide range of activities. To solve this problem, an ASTM project was developed to create a standard guide for laboratory information management systems. That guide has been available for several years and was most recently updated in 2006. It is still a good guide for understanding what a LIMS is, what kind of entries a database might contain, and the process of using or purchasing one. Since the systems first became available, a lot of work has gone into their development in general, as well as versions for specific markets. There are LIMS tailored for environmental, product stability, and formulation testing, as well as other applications. Each of these has facilities to make it easier to work in a particular application. For example, in product stability testing, you're concerned with determining the shelf life of a product or the effect of temperature and aging on a formulation to see if it breaks down over time. In order to do this, an array of tests is automatically set up to look at certain product characteristics periodically over time. In traditional LIMS, each set of tests for each sample over the time period of interest would have to be added one sample at a time. In a system designed for stability testing, the basic characteristics of the project would be laid out for the samples and test requirements automatically filled in. The chart on the screen shows some of the elements that the database is built around, as well as the connections to other software and laboratory functions. Going through the contents of the chart at this point would be a lot more detail than we can afford. If you're interested in looking this in more deeply, you can purchase the guide from the ASTM. There are a large number of products available for this application. The illustration you see on the screen is an example of one. This product has a graphical layout that helps you understand how the system can be used and understand the information it contains. For example, It shows the sample status for all samples in the laboratory. As you can see, there are none that are on hold, 414 samples that have arrived, 5 that are awaiting preparation, 421 that are available for testing, 230 that have been completed, and 15 that are waiting for inspection. This kind of detail greatly assists lab managers in understanding the lab's current workload and planning each day's work. One of the issues that needs to be addressed, or at least understood, is the impact that software like this can have on a lab's operations. Properly planned and implemented, it can greatly facilitate a lab's operations. However, if there are organizational problems or problems with how the laboratory operates, implementing these systems can freeze those problems into the software, because people tend to modify software to fit existing behaviors in the laboratory. Before systems like this are considered, a laboratory should review its practices and make any changes that are needed. When you are considering a LIMS, you should have a thorough understanding of the problems you want to address, including both short and long-term issues. Don't go into the process with the assumptions that a particular product or technology is the answer to the problems. Make sure you objectively determine what the requirements are, and then look for products that meet those requirements. The failure to fully understand and state product requirements is one of the leading causes of project failures. It is also important that you talk to the people that work in the laboratory, because they will be affected by the implementation of any database software system. They may have concerns that need to be addressed, and the ideas and improvements that are needed to be made both organizationally and in terms of software features. When considering these types of products, be careful of getting in over your head. These are expensive systems and take a lot of planning to put in place. If necessary, look for consultants that can help you. Be skeptical of every claim the vendor makes. Ask for proof of the claims and ask for reference sites that demonstrate the points the vendor wants to make. Talk to people who are using these systems. Get educated. Ask lots of questions and don't assume anything. If there's something you don't understand, don't gloss over it. Ask until you're satisfied with the answers. Talk to the users of the products that you're considering. If possible, see if you can visit their facilities and see the products in actual use. Vendors often have users groups. Ask if you can contact them, or if timing permits, attend a user meeting. When you try to justify the purchase of a LIMS, look outside the laboratory. The work in a testing laboratory is done in support of other groups. Could the purchase of such a system, with faster reporting, and the potential for the ability for users to look at the system to find out the status of work, be of benefit to them? There is an opportunity to improve not only the laboratory's operations, but other organizations as well. The reasons for failures of LIMS projects are typical of most large-scale software projects. They include such things as scope creep, the constant changing of user requirements as people learn more about systems and what can be done, implementing the wrong technology, such as making assumptions about network systems or access to a product over the internet, for example. Those types of implementations might prevent needed interactions between instruments and database systems from occurring. Other factors include inexperienced project management, projects that are too ambitious, a lack of commitment to the project's success, and finally, but far from least, a failure to properly determine systems requirements before commitment to a product is made. Improvements in laboratory workflow could happen if laboratory instruments send data directly to the LIMS. This is a fairly common requirement, and a number of vendors have included these capabilities in their systems. Often the capabilities are limited to instruments from specific vendors or possibly particular models of equipment. Going beyond the capabilities that are provided by the vendors can be an expensive undertaking, and doing so can jeopardize the project. If this is key to your product requirements, make sure you carefully consider what has to be done and your ability to carry it out. Often there are announcements of partnerships between various vendors to solve these types of problems. One vendor's instrument management system may be paired with another vendor's database system. One thing to look at is whether or not these pairings are done for marketing purposes or if they are built upon a solid technical basis. Marketing partnerships come and go, but if you're purchasing a product based on these partnerships, you'll have to live with it. We are now going to turn our attention to the second major laboratory informatics product set, Electronic laboratory notebooks. Electronic laboratory notebooks are a replacement for the traditional paper laboratory notebook that scientists and technicians have used for generations. The paper laboratory notebook has some features that we need to look at in order to understand the benefits of the electronic versions. First of all, they are used to contain all laboratory data. That might consist of handwritten notes, equations, drawings, as well as material printed from other equipment that is taped to the notebook page. On the bottoms of the notebooks there are spaces set aside for the signature and date of the person to whom the notebook is assigned, and also for the signature and date of the individual who is responsible for reviewing the scientist's work. This dual signature arrangement is important because it establishes the timing and authenticity of laboratory work that may be used as part of corporate intellectual property. It may find its way into the patent filings, new drug applications, or as test results in support of research projects. The limitations of paper notebooks include the fact that it is on paper and as a result easily damaged by moisture, mold, or other mishaps. It's also difficult to search. Even digital copies suffer from the fact that you have images of someone's handwriting that can be hard to interpret. As notebook pages age, people forget what's in them, and as a result, intellectual property disappears simply because it's forgotten. Unlike LIMS, there is no implied process that supports electronic laboratory notebooks. They are a recording device. In order to understand what kind of product you will use for these applications, you really have to understand how the laboratory's work is done and what its specific requirements are. Vendors see this area as one that is ripe for development. A wide range of products have been suggested, including, for example, Adobe's Acrobat portfolio product. Because of the wide range of applications that a notebook can fill, even very simple products might suffice, since in some cases, a laboratory notebook is nothing more than a diary or journal. Since we are talking about electronic systems, laboratory notebooks can be viewed as places where programs or scripts can be executed to capture laboratory data, provide support for regulatory requirements, and meet the needs of specific types of laboratories such as testing and quality control or quality assurance organizations. Just as a LIMS was viewed as the organizational hub of a testing laboratory, electronic laboratory notebooks can be viewed as the organizational hub of a research facility. This is a dynamic area of product development, and saying too much about specific products is likely to put that material out of date quickly. On the screen you see two references that have done a good job of keeping information about these products up to date. Electronic laboratory notebooks consist of three classes of products. They include general purpose, discipline specific, and script execution systems. As mentioned earlier, notebooks are essentially diaries and can contain written information, audio notes, images, charts, basically anything that can be put into a file. They act as a means of intellectual property management and are searchable, which provides a major advance over their paper predecessors. In addition, since they are in electronic form, they can be easily backed up and as a result preserved against loss. As you can see from this request, people's requirements for laboratory notebook products can range from the very simple to the very complex. For some people's use, a product such as Microsoft Word may be all they need, since Word's very flexible format can include text, charts, spreadsheets, drawings, audio files, video files, and a wide range of information that can be captured in electronic format. As a low-cost general-purpose diary or journal, a product as simple as this has a lot going for it. When we get to application or discipline-specific laboratory notebooks, things change drastically. We have the same requirements as a general-purpose system, with the addition of features that make it easier for the researcher in a specific area to do their work. For example, a chemist may want a notebook that has links to chemical structure databases or reaction databases, making it easy to reference research material without having to enter it manually. A biologist might want access to reference databases that support their work in much the same way. It may include specialized dictionaries or templates for filling out data and observations. When we make this jump from the general purpose to the discipline specific, the nature of the product and its cost change significantly. One of the earliest application-specific notebooks was from Wolfram Research in their Mathematica product, which supported text, equations, mathematical graphics, automated equation solving, and animations such as the one on the screen which shows a device that can drill a square hole. The use of electronic formats opens up a world of possibilities. An important one is the ability to share information between researchers who are collaborating on projects. This vastly increases the complexity of the product and the requirements of the system needed to support it. The third type of system is that which provides scripted execution of laboratory processes. These systems are used in laboratories which are running the same procedures day in and day out. They are an electronic guide to every step of the process, guiding the technician in the work, recording data, electronically checking the availability of equipment for the processes, as well as reagents and chemicals used. In most regulated environments, equipment used for testing has to be periodically calibrated and evaluated to make sure that it's working properly. In addition, chemical solutions that can age and change their properties have to be periodically evaluated to make sure that they are suitable for use in an analysis or procedure. These electronic systems keep track of equipment calibration and reagent characteristics to make sure they're suitable for use, avoiding having a technician running a test with equipment that is not in good working order or chemicals that are out of date. In those cases, the results wouldn't stand up to challenges and could jeopardize a research project. In addition, systems may provide links to instrumentation and automatically pull data in as measurements are made. They're also designed to provide all the information needed to support regulatory compliance. Systems with this kind of capability are available as standalone products, as well as lab informatics systems with scripted execution functionality built into them. Some LIMS vendors have included programming capabilities for scripted execution into their products. These systems often are not as robust and detailed as standalone systems. As you might expect, there are advantages and disadvantages to including the scripting capability in a LIMS product. On the plus side, the programmer has access to the full database elements, consisting of all the test request information, sample description, and results. As a result of having both LIMS database and scripted execution in one package, there is no secondary process of transferring the data from the scripted execution functions into the database. Also, you're working with an all-in-one product, so no additional software is needed. On the downside, someone has to program the system and validate all of the interactions to show that the system is working properly. All of the regulatory issues that support software design and development apply to this work. The level of sophistication of the system is up to the user and limited by the programmer's capabilities. In addition, programming errors can compromise the database, so development has to be done on a secondary system so that laboratory work in progress isn't compromised. Some of this development work can be done using virtualized software, but that could remove the ability to interact with instrumentation. Standalone systems have their strengths and weaknesses as well. You have vendor support and pre-scripted methods to work with, reducing the amount of work you have to do if a method that you need is available for that system. If the system supports instrument communications, another major user requirement hurdle has been dealt with for you. And like most software packages, the vendor is going to be constantly improving the quality and content of the software, which benefits you as well. The systems also have a framework in place for method development and vendor support to assist you in your work. These systems are currently usable by less technically savvy users. A downside, unless the vendor supports it, is a need to arrange for communication support with a LIMS or enterprise resource planning system. Depending on your requirements, this most likely will involve additional programming. You'll also have to purchase additional software to complete scripted execution and sample management, since you're dealing with two software packages. VelQuest is currently one of the leading suppliers of scripted execution systems. They provide both instrument interfaces and links to database systems. Their system includes automated data capture in a method viewer that allows you to inspect the progress of the method as the analysis proceeds. For any given test procedure, you can quickly scan the work and see if there are any flags raised about its progress. Audit trail information, out-of-limit specification flags, equipment or reagents being out of date, and any annotations can all be viewed. If you want to look at the source data for a particular test, it can be very easily brought up. However, there are some limitations. For example, the information on the chart on the bottom of the page is limited in quality to that produced by the instrument print output. You can't zoom in and look for more detail. Laboratory informatics has become a very complex field with a large number of choices for products depending upon your needs. To make matters more complicated, competitive pressures are causing vendors to merge capabilities. In some cases, it's merging things such as scripted execution into a LIMS system. In others, it's an attempt to create an all-in-one style product that addresses all the needs of a lab's information handling. The lab needs to consider the trade-offs between the compromises that will exist in all-in-one products and the work needed to integrate best-of-breed product selections. When you are making informatics choices, you have to make decisions not only based on product requirements, but also on implementation technologies. For example, do you want systems hosted on-site, or do you want to take advantage of a vendor's networked access offerings? One way of addressing the choices involved in products is to look at laboratory workflows. The diagram you see on the screen shows a basic workflow for the use and development of laboratory knowledge, information, and data. The ovals represent databases and the arrows represent the processes that are used to read elements from one database, process them, and then put the results in another database. For example, if you're running a testing laboratory, the knowledge database would contain all of the documents relating to that lab's operations, including test methods, hazardous materials handling, chemical inventories, personnel records, and so on. If we're running a test, we would read the test procedure from a document in the knowledge database, do the processing as part of the measurements and experiments process line, record the data in the instrument database, carry out a data analysis, and with the results being stored in the laboratory information management database. Testing laboratories, and in particular quality control, would omit the synthesis step for the creation of new knowledge, which usually occurs in research and method development laboratories. If we apply that workflow to a testing laboratory, we can place some product classes to see how they fit in. Testing laboratories get samples from somewhere, and when the results are done, send them back to whoever submitted the samples. That explains those two blue arrows in the middle of the screen. In applying products, we might use a scientific data management system for the knowledge database, a laboratory information management system for the information database, and an instrument data system for the laboratory's measurement database. In addition, we might use a script execution system to help guide the experiments that are being done in the lab. As a result, using a workflow model like this, we get a pretty good idea how products fit, how they need to connect to each other, and begin to derive product requirements. For example, we may want, as part of the product requirements, to automatically have the results sent to the sample submitter instead of requiring the analyst to carry out that as a separate step. In addition to looking at product capabilities and requirements, we also need to be aware of how systems are going to be implemented and what kind of technologies we want to take advantage of. There are a number of trade-offs that can be made between cost, ease of implementation, security, and other factors. The workflow diagram we looked at a few slides ago isn't a two-dimensional structure. It has depth. For example, the process elements are built on layers of software, as are the database systems, all connected over a communications network. That network can connect elements on the lab bench, shown on the bottom of the diagram on the lower right, systems used to manage the laboratory in the middle of the diagram, with connections to other laboratories and departments within an organization. When we are connecting systems to networks, we have to be aware not only of the local impact, but the impact on the entire network as well. One technology that is being offered by several informatics vendors is that of software as a service. The benefits to the user are speed of implementation. Since they are running the system from the vendor's site, the implementation is basically at no cost. This also means that the system can be put into service very quickly. All interaction with the system occurs over the network. While those are significant benefits, particularly for small labs that may not have extensive information technology support, there are some downsides. While technically instruments and other laboratory systems can be connected to these remote systems, from a practical standpoint that may not be a good idea, since delays in network transmission, power disruption, or other failures can alter the effectiveness of the system. Another consideration is system security. The fear is that because of all your data is being stored on remote systems, that security may be a problem. The vendor will claim that security is probably no more of a problem than it is on the organization system. While they may have a point, any site that holds confidential information is going to be a target. Recent experiences have shown that even highly secure sites can be compromised. The only way to be sure of security is to disconnect the lab's network from public access systems. As with anything else, there are trade-offs. On the plus side, the software as a service model provides a quick startup with minimal investment. It can be used as an extended test drive of the system if you're considering the product for purchase, and gives you a chance to gain some experience and provide training while an on-site implementation is going on. On the downside, as we've noted, there are questions about security and the ability to connect to other laboratory systems. When people are dealing with laboratory informatics products, the focus has too often been on the products themselves. Emphasis needs to be put on overall systems design and engineering. Companies need to learn how to plan and design laboratory systems, taking into account the effects of one system on another, and approach the development of laboratory information technology in the same way they would plan for manufacturing systems. One question that pops up frequently is whether the need is for a laboratory information management system or an electronic laboratory notebook. The real question should be, what problem do you want to solve? The software packages provide different capabilities addressing different needs. The lines between packages are being blurred due to mixing capabilities and efforts towards shifting laboratory information management system functions to ERP packages. This latter point can be a bit of a problem. For one thing, it mixes laboratory data with production data and can cause problems with system security and access. It breaks down a barrier that should exist between production and quality control, that is, controlling the availability of data until it is reviewed and approved for release. It also means that changes to the system, including upgrades, can have a drastic effect on laboratory operations, particularly if instrument connections are made. The problems that can result from the implementation of laboratory informatics systems and integration can be reduced by making sure that we understand the way labs should work, fix organizational problems before software is implemented, develop a solid plan for informatics usage, and choose products that clearly fit a defined need. Planning is essential, and before you purchase a product, people need to go to training to learn how to use it. This can be expensive, but during training you have an opportunity to learn more about a product, possibly finding benefits that you weren't aware of or weaknesses, and be better informed and prepared to complete the planning process. You also have to be careful about attempting to force-fit products together. This may result in a successful solution on a temporary basis, but can fall apart when changes or upgrades are required. You also need to be wary of marketing solutions to technical problems. In addition, you need to take a look at whether to deal with product integration yourself or using products that have been integrated by the vendor. You also have to look at how informatics products will improve the operations of the lab's work environment. Products have to fit the process. Changing the process to fit the product can have unfortunate consequences, including concerns over regulatory issues about previously validated methods. There may be an interest in buying a single product such as an electronic laboratory notebook and applying it across all laboratories. From the standpoint of cost and support, this would appear to be a very efficient approach. However, from a functional standpoint, research and testing laboratories may have very different requirements. If the organization supports more than one scientific discipline, a single product implementation may not work. You also need to take into account the different groups that need access to the knowledge, information, and data that are developed in laboratory work. Standardize where possible, but not at the expense of inhibiting laboratory work. For example, all testing laboratories might use a similar laboratory information management system. So far, we've dealt primarily with the technical aspects of products. There is also a human dimension. The people working in the laboratory need to be part of the selection process. They will be directly affected by product choices and implementation and need to understand what is being done, why, and the impact it will have on their jobs. Make sure their training requirements are being addressed and get their input on product requirements. They may be aware of things that management isn't, and those points could have an impact on the project's success. Start people's training as soon as the need is established and the number of candidate products has been narrowed down. It should be done as early as possible. In a July 2011 survey by Lab Manager magazine, a third of the responses listed staff issues as a major challenge for electronic laboratory notebook implementation. An earlier survey showed that educating laboratory personnel is a high priority. When considering laboratory informatics systems, there are other points that you need to review. How long will you need live access to your data? This may have an impact on the type of technologies that you use for implementation, including backup strategies. How long will your vendor be in business? The laboratory market has seen a lot of mergers and acquisitions, and these can put product maintenance and support strategies in jeopardy. This is a particular concern if you're considering all-in-one product strategies. Do you have a data migration strategy? If a product is upgraded or replaced, can you extract the data and move it easily to a replacement system, or is this going to jeopardize the operations of the laboratory? When evaluating your laboratory's informatics needs, one consideration that comes up is whether or not you should buy commercially available products, or is it more cost-effective to build one for your laboratory program? This question first came up when hospitals were considering laboratory information systems, functionally equivalent to industrial laboratory information management systems. One study concluded that at best, an in-house built system would approach the capabilities of a vendor-supplied system, but only for a short time. Vendors were much more capable of improving products than in-house technology groups. This issue resurfaced when laboratory information management systems became popular in industrial laboratories. Again, while some labs may have attempted to build their own systems, the majority chose to purchase commercial products. That same build or buy question is coming up again with regard to electronic laboratory notebooks, and this time with a bit more justification. The idea is that electronic laboratory notebooks can be used in all laboratories, where LIMS are only used in testing labs. With many companies having geographically dispersed operations, they have a need to protect intellectual property while providing broad access to information. In addition, scientists in different groups may be collaborating on projects. With the prospect of a number of system installations and the need to control access to research results, the idea of in-house built systems is attractive. The economies of scale could favor such developments. Small and medium-sized companies should avoid the temptation to build their own electronic laboratory notebook system. They will probably get better support, a higher quality product, and broader functionality from vendor offerings. In large companies that have the resources to fund and manage such a project, there are other concerns that need to be addressed. Is there enough common agreement among laboratories on the functionality for an in-house built electronic laboratory notebook system? It may be possible to build a layered structure which has a common underlying database with a discipline-specific layer on top of it that can be customized to suit the needs of individual laboratories. While those words are easy to write down, making them happen is a big job. If your information technology support groups don't have a good track record on smaller projects, they'll never tackle this one. By building your own in-house systems, you have a single vendor solution that is limited by the underlying platforms of both operating system and hardware. Do you want to deal with single vendor solutions? Do you have the ability to support these products over the long term? There's also a question of your ability to keep up with the functionality of vendor-supplied products. They are your competition. Your lab people will see desirable features popping up in vendors' products, and they're going to want to see them in yours. Can you keep up with the continual stream of requests for new functionality and product upgrades? Finally, not only will you have a single vendor solution, but you will have to form your own pool of people to support and manage the system. There won't be any outside resources to draw on with prior experience. They will come into the company without any understanding of the product and have to be trained before they can be effective. Projects of this magnitude can take a long time to develop. What are your laboratories going to do to manage their lab work while the project is under development? Are laboratory managers willing to sacrifice effectiveness and productivity for the promise of an in-house developed system? Are you going to have to use a vendor-based product as an intermediate step? If so, how will you make the transition between the temporary solution and a long-term product? Laboratory informatics is no longer an option in modern laboratories. It is a requirement. Meeting that requirement takes a lot of planning, training, and support. Before you attempt to satisfy the laboratory's need for informatics solutions, make sure that the organizational problems have been solved. Get the politics out of the system. Do an evaluation of the laboratory's operations. Take a look where the laboratory really needs to go, where it is now, and map out a plan to get where you want to go. Use operational workflow models to map out not only the lab's workflows, but how those workflows interact with other groups. This last point can be used to build support for your proposed programs. Problems that occur in product selection and implementation on the lab bench can be severe, but have a relatively short-term impact. They can be fixed without disrupting the overall lab's operations. Problems that occur with laboratory informatics systems, because of their cost and the time it takes to implement them, are going to have a major long-term impact. They can't be replaced easily and require a migration strategy to move from one to the other so that you minimize the disruption in laboratory work. Laboratories have to move away from the idea that laboratory automation is a collection of individual products and technologies. The systems relate to each other and have an impact across the laboratory when changes are made. Part of management's responsibility is to develop an overall architecture for laboratory automation technology usage. That includes the development of policies and practices that guide the planning and implementation of laboratory systems and workflow models that guide product selection. Laboratory work deserves the same level of attention as any major organizational data and workflow management application.